This is Brian Putt. Today I'd like to talk to you about a value of information mind problem. It's called the frog problem. You can actually look up solutions of this, other solutions of this on YouTube, but I want to look at it a little differently. Let me describe the problem. First of all, you are walking in the forest and along comes a mushroom and you decide to eat it. Well, it turns out it's a poisonous mushroom. And the only way you can live is if you immediately kiss a frog, a female frog. And you look behind you and you see this frog and it says, kiss me, kiss me. So that's one option. You could go kiss that frog, but it could be a male or a female. You don't know. You look the other direction and there are two frogs. And you don't know whether they are male or female either. And we also know that the male frogs croak. So if there's a male frog there, it will croak. So the question is, to live, you must kiss a female frog. Do you kiss the two frogs on the left or the single frog on the right? You can only have time to go to either the left or the right. So either to kiss two frogs or to kiss one. Which do you want to do? Let's look at this problem using simulation. This is different from the solution shown on the YouTube now. And also I want to test the sensitivity of our decision to the probability of a female frog. What is the population, the female frog population? So let's go look at the model and see how we did the analysis. First of all, we have the probability of the female frog. We're going to look at a sensitivity to that. First of all, we have to simulate what kind of frog is on the left and the right. So on the right side, there's one frog. And so this simulation here decides whether it's a male or female. A 0 indicates a male frog, and a female frog is indicated by a 1. On the left side, there's two frogs, so I have two of these variables. In this case, there are two females. And then I formed a metric, 10 times the first frog plus the second frog, so in this case, it's 11. Now, there's a little trick here to solving this problem, because this is really a value of information problem. And we're going to see how to use the chance of whatever in SIPMath to get some of these probabilities. So given this metric, I now want to understand if I hear a croak, that means there cannot be two female frogs. So what I'm going to do is say, if this metric is equal to 11, I'm going to blank it out. Otherwise, I will use this metric. Now, for those that are familiar with SIPMath, we can go over to this PM table here, and we can see the results of this, well, I'll call it a conditional SIP. Because what I've done is actually removed, here you can see, here's the metric SIP, and over here is the metric given we hear a croak. And you can see that I blanked out all these 11s. Well, what good is that? Well, I've now changed the population of that SIP. It eliminates the two female frogs. So now, let's look at the chance of living. So if I go to the right, the chance of living is that the metric, which is this metric right here, is greater than 0. And the answer is 51. And that's because the female frogs are coming in 50% probabilities. What is the chance if I go to the right if I don't hear anything? So there could be possibility of two female frogs. Well, here it also is the probability being bigger than 0, which would be two males. And that answer is 75. And once again, it's looking at this metric of two frogs. Down here, I'm looking at a chance of success that we hear a croak. And that means that I'm going to look at this metric which doesn't include any female frogs, 2 female frogs, and ask the question, what is the chance that I have at least 1 female frog? In this example, you get to kiss both frogs, by the way. And that answer turns out to be 67. Now, then we have to make a little correction to the count of whatever, because the count of whatever, the chance of whatever, chance of whatever, divides typically by PM trials. I'll tell you what, I'm going to redo this one here so you can see how that's done. SIP math, chance of whatever, this value metric is greater than 0, okay? And it gives me 50%. But that is the wrong answer because I divided by all trials. I only need to divide by the trials that are active. And that is the count of this SIP. And to change that E18 to a SIP name, I go here and say get stats. And now it says 67. So divide by the count, a metric given, we hear a croak. So that is the right answer. Now, so we can take this result and we can look at these distributions. Here it's 25% each for these 4 possible outcomes of male, female. And over here is the probabilities given we hear a croak. And you'll notice there is no female, female. In other words, an 11 over here. That's been eliminated. Now something else I did is I wanted to look at the sensitivity of the probability of the male frog. What is interesting here? Here is if I pick the the right side with 1 frog, it's just a linear line. In other words, at 50%, there's a 50% chance that I have a female frog. At 80% chance of a female frog, I have an 80% chance of living. If I have no information to go to the 2 frogs, it follows this blue line. Okay? And we saw before where if I had a 50% probability, it's 75%. That's what we see here. Interestingly, when I get information that there was a croak, it actually reduces the probability of living. The red line here is below the blue line. We normally think of information as adding value. In this case, it's negative information, and therefore it's reducing the value of the problem to us. So I found that interesting in looking at this. So I hope you find this of interest. I think the simulation affords an opportunity to examine these problems in more detail and look at sensitivities. Another sensitivity is, what if there was a probability that the frog croaked? Or what is the probability, or how does the chance that you might hear 2 croaks impact your decision? So these are things that can be studied with the simulation model pretty easily, whereas it becomes a little bit more complicated when trying to solve this in closed form solution. Thanks for watching.